Hi, welcome to Dr. Lunga's Math Lab. I'm Lunga Ulu. I'm a neurosurgery registrar and I also like mathematics. At the Math Lab, we don't aspire to equip you only with the practical skills you need to pass an examination. We will do that, but while we do, we'll also pull back the curtain on the wonder that is mathematics and show you that it's not just a list of steps to finding an answer, it's also an education in one of humankind's greatest endeavors. Today, we're taking our first steps into the 4,000-year-old tool that allows us to deal with manipulation of symbols in unknown quantities, one of the unifying threads that holds together almost all of mathematics. I'm talking about algebra. "4,000 years ago is a convenient time to place it because that's when the earliest written record of algebra surfaces. But what does 4,000 years actually mean? Well, if we went back 4,000 years and landed in Eurasia, we'd probably find the Botai, the nomadic inhabitants of Eurasian steppes, trying to tame horses for the first time. Only a handful of pyramids had been built, and around this time, the last of the woolly mammoth died on Wrangel Island, and it probably dates back even further beyond that. Around this time, nestled between the rivers Euphrates and Tigris, cities started developing in a region now known as Mesopotamia, Meso meaning between, and Potamoi meaning river in ancient Greek. In these cities, by far the most important of which was Babylon, the first seedlings of algebra are found. Over 1,000 years, these cities invented a system of proto-socialism where farmers contributed their produce to public storehouses, out of which workers not primarily involved in agriculture, like blacksmiths, builders, and administrators, could be paid for their services in grain. It's tempting to speculate that this ever-increasing complexity in their way of life spurred them into inventing tools like algebra to keep track of things and predict the future using historical data. They weren't using the same symbols or ways of representing the numbers, but the ideas were the same. If we fast forward in time, we find major contributions from mathematicians originating from all over the world, like one Greek mathematician living in Alexandria in Egypt, going by the name of Diophantus, who authored the treatise Arithmetica, which is the first work known to employ algebra as we know it. It also inspired the rebirth of the field of mathematics called number theory, which is concerned with the properties of positive integers and is among the oldest areas of mathematics. A little further on, in India, we find another mathematician by the name Brahmagupta, who was the first to give rules to computing with zero. Some consider either one of these mathematicians the father of algebra, but one name towers above them both, at least with respect to algebra, and that's that of Persian mathematician Muhammad ibn Musa al-Khwarizmi. Born around 780 AD in Khorasan province of Persia, now Uzbekistan, al-Khwarizmi made contributions to the field of geography, astronomy, cartography, which is the study and practice of making maps, and improved upon the existing design of the sundial. By the time he died in 850 AD, he had cemented himself as a legend, and this book is the reason why. The word algebra comes from the word al-jabr, which means restoration or completion, and it appears in the title of al-Khwarizmi's book, which translates to the compendious book of calculation by completion and balancing. This book is significant not only because it gave this field of mathematics its name, but many of the modern ideas fundamental to algebra, like the balancing of an equation, were codified in it. So what is algebra? What is it for? How does it differ from arithmetic? Is there a difference? I want to introduce this to you by way of example. Gina, our mechanical engineer friend, is out shopping. She's going on a date, and even though she could just wear the hero costume, she's worried it might send the wrong message. She goes to a clothing shop and is delighted to see that everything in that shop is 50% off. She finds a pair of shoes that she likes and it costs 3,000 Rand. Her discount on this particular item would be 50% or 0.5 times 3,000. That's arithmetic. The discount price is therefore 1,500 Rand. But she's at the shop, she's got the cash, why not splurge a bit more? Let's say you want to generalize a little bit. However much an item costs in this store, there is always a 50% discount attached to it. It could be a bracelet, a blouse, a jersey. All these things cost different amounts of money. It's no longer a constant, that is, no longer holding the same value, but it changes. We say it's a variable. could assign some placeholder to let us know that it could be any item at the shop, to which you could apply the discount. You could assign any symbol that you want. It could be X, it could be Z. For this example, let's say X is the non-discount price of the item, the thing that can change depending on what item Gina wants to buy. So our discount price would be 50% times X, or 0.5x. So what do we have? You give her the price of any item in this very generous store, and Gina can substitute that price for X and work out what the discount price will be. That's a very simple example, almost too simple, but that's the essence of what algebra is for. It allows us to be abstract. Let's add another layer to this. Does the discount have to be 50% all the time? No. Sometimes it can be 30%, other times 10. So what do you do in that situation? Well, we've already done it with the items of clothing. Instead of staying the same or remaining constant, it has now gained the ability to change or vary. Therefore, we say it's a variable. That means instead of giving it a value like 50% or 0.5, we assign to it a symbol that we understand to mean that this value can change. Let's say, for the sake of argument, the possible discount is Y. Knowing this, we can work out the discount price of any item by multiplying the discount percentage, Y, and the item that you're trying to buy, X. We get that discount is Y times X, or the discount equals YX. We don't have to use the word discount either. We could use any symbol that we assign it to. For example, D. We could say D equals XY. This brings us conveniently to the topic of algebraic expressions. Let's say we have expressions 7 times 2 to the power of 5 and 3a to the power of x. Which do you think are the bases here? It's obvious, right? 2 and a are the bases. So why isn't it 7, 2, and 3a? Or 2 and 3? Well, it speaks to the structure or anatomy of an expression with an exponent. Each expression has a base, an exponent, and a coefficient. The coefficient is the number that stands in front of a variable in a term. So here, which are the coefficients? 7 and 3. The exponents are 5 and x. I know you already know all of this. Mentioning exponents allows us to segue right into trying out some of this algebra. This is my favorite part of the video, the part where we get to practice some problems. But before we get started, please like and subscribe for the YouTube algorithm. It really helps a lot. Here are the laws of exponents. I've deliberately refrained from naming or numbering them because we tend to get caught up in associating names with formulas that we forget the formulas themselves. The first two I want to mention are called the rules of exponents in algebra. Namely, that x to the power of 1 is equal to x and x to the power of 0 is equal to 1. They tell us that any number raised to the first power is itself, and any number raised to the power of 0 is 1. As we know, exponents allow us to multiply something by itself. We also know that integers can have negative values. So can you raise a base to a negative exponent? How do you multiply something by itself a negative number of times? Technically, you can't, but the next law was crafted to help us get around that. Law 3 states x to the power of minus n is equal to 1 divided by x to the power of n. The reason this is true is a negative number is the inverse of its positive counterpart, and division is the inverse of multiplication. So a negative exponent is essentially repeated division. So x to the power of minus 1 would be equal to 1 divided by x. X to the power of minus 2 would be equal to 1 divided by x divided by x. X to the power of minus 3 would be equal to x divided by x divided by x, and so on. Mathematicians have agreed that instead of denoting it as 1 divided by x divided by x, it's more elegant to write it as 1 divided by x multiplied by itself a specified number of times. It works out to the same thing. Let me prove it to you. Let's say we have 4 to the power of minus 3, or the negative third power. This would be equal to 1 divided by 4 divided by 4 divided by 4, which we could use our calculator to show is 0.015625. If we retrace our steps and say 4 to the negative third power is equal to 1 divided by 4 times 4 times 4, we still get 0.015625. The next law we're going to deal with tells us how to take a base raised to an exponent and raise it to another exponent, or stated another way, when one base shares two exponents, you can ignore the base and multiply the exponents. The rule states that if we have x to the power of p grouped in brackets and raised to the power of q, that equals to x to the power of p times q. For example, let's say we are given m exponent 2 in brackets 2 exponent 7. According to the rule, m is equal to the power of 2 times 7, which is 14. What if it's something slightly more complex than that, like 5 times 4x cubed to the second power? The exponent applies to every term within the bracket, so you have to apply the exponent to the x to the third and to the 4, which gives you 5 times 4 squared times x to the sixth. This simplifies to 5 times 16 times x to the sixth, and lastly multiply out the bracket and you get 80x to the sixth. The next two sets of laws are about multiplication and division. We'll treat them as two sets of 2. The first pair of laws relates to scenarios in which the bases are different but the exponent is the same. These laws are about how you can distribute or undistribute an exponent to different bases. The second and last pair deals with scenarios in which the bases are the same but the exponents are different. Let's start with the first pair. The first law says that if you have x times y raised to the power of p, you can rewrite it as x to the p times y to the p, meaning that you can distribute the exponent to every factor in the group. You already saw me do that in the previous example. The second rule shows, in brackets, x divided by y, that's been raised to the power p. It says that you can rewrite it as x to the p divided by y to the p. In other words, you can distribute the exponent to each part of the fraction. These laws also work in reverse, meaning you can undistribute them if they are the same. For example, let's say you are given x cubed times y cubed. You can rewrite the entity as xy cubed. If you have the expression x cubed divided by y cubed, you could rewrite the expression as x divided by y cubed. The first law states that if we have x to the power of p multiplied by the same base x to the power of q, we can combine them simply by adding the exponents together. The second law states that if we had x to the power of p divided by the same base x to the power of q, we can combine them simply by subtracting q from p. Let's work through a simple example to drive the point home. We have 3 cubed multiplied by 3 to the 4th. Our law tells us that this would equal to 3 to the power of 3 plus 4, which is 3 to the 7th. Is this true? 3 cubed is 3 times 3 times 3, and 3 to the 4th is 3 times 3 times 3 times 3. That's 3 multiplied by itself 7 times. It's confirmed. This makes perfect sense when we consider that an exponent is telling you to do this exact thing. It's telling you to multiply a base by itself. If the base is the same, you can simply add the exponents together. Here's one last example. We have 6 cubed divided by 6 squared. Our rule says this equals to 6 to the power of 3 minus 2, which is 6 to the first. We can check if this is true. 6 cubed is 6 times 6 times 6 divided by 6 squared, which is 6 times 6. Doesn't this look familiar? Since all the bases are the same, they form pairs above and below the division sign that can be cancelled out, so it checks out. And there we have it, the rules of exponents. Let's check in on Dineo. She's been at the computer lab working on a top secret cryptography system. She's not able to tell me much, but exponents are quite fundamental in cryptography. As Dineo would tell you, there's no such thing as a completely secure computer system, and system architects realize this. They employed a strategy known as security in depth, in which attackers would have to overcome numerous obstacles, sort of like penetrating a vault in a bank. First, you would have to tiptoe around a pack of guard dogs, evade a security guard, disarm the alarm system, somersault through lasers, and finally somehow break through a 2-ton door to get the gold within. Here's the logic behind passwords. When you are asked to create a password of a certain length and combination of symbols and elements, all the possible options available fit into each spot or location. Let's say they said only use 6 lowercase letters. There are 26 letters in the alphabet and 6 locations, so there are 26 to the 6th possible combination. That's a touch under 309 million possibilities. But if they had said use upper and lowercase letters, use 10 digits and 10 symbols like @ or exclamation points, that number grows to 72 to the 12th power. That's more than a sextillion. That's a number so large, I bet most people wouldn't know there's a name for it. It's more than 62 trillion times the size of the 6th lowercase letter password. A computer running through all those possibilities would take 62 trillion times longer, and it makes it very impractical. That's the power of exponents. Now I think we should do a few problems, something to really get us thinking. We've been laying the groundwork of simple ones. Now let's test how strong that foundation really is. Here we have 2 to the 4th times 4 to the 3rd times 8 squared. How shall we tackle this? I think the best way to proceed is to try and get them all of the same base. Here it looks like the best base would be 2. So we have to state 4 and 8 in terms of the base 2. Can we do that? Of course we can. The expression becomes 2 to the 4th times 2 squared to the 3rd times 2 cubed to the power of 2. We just have to multiply the exponents, giving us 2 to the 4th times 2 to the 6th times 2 to the 6th. From here, we add the exponents because we are dealing with a shared base and we are multiplying. This gives us 2 to the 4th plus 6, which equals to 2 to the 16th. The next problem is a little bit more challenging, but I'm certain we can handle it with ease. We have bracket 2x to the 5th times y squared, another bracket 7x cubed times y to the 4th, last bracket minus 5x squared times y. This isn't actually as difficult as it first looks. It's actually an exercise in multiplying monomials. When you tackle this problem, you just multiply the like terms with each other. So here you get 2 times 7 times minus 5, which gives us minus 70. That one is done. We put it where it belongs at the front. Next, we confront x to the 5th, x cubed, and x squared. We know that using the rule of multiplying terms at the same base, that all we need to do here is add the exponents, which gives us 5 plus 3 plus 2, which gives us x to the power of 10. How's that? You're getting it. Finally, the y. We have y squared times y to the 4th times y. This gives us y to the power of 2 plus 4 plus 1, which gives us y to the 7th. Our answer is minus 70x to the 10th, y to the 7th. Let's do one more of these. How about this one? We have 3a cubed plus 7a cubed over 5a squared. Let's give that one a whack. So above the division sign, we have terms that are identical, a cubed. That means we can add their coefficients. So we get 10a to the power of 3 divided by 5a squared. The coefficients can be addressed with normal division, giving us 2a cubed over a squared. Using division exponent rule, we have 2a to the power of 3 minus 2, which gives us 2a, and that's all there is to it. Let's try another one, but let's make it a bit more interesting and see how we do. We have in brackets 2x minus 3 divided by x squared. Now you can be fancy and do all of this in your head, and normally you can, but with this one it's going to be a bit difficult to be 100% sure of our accuracy. I'm just going to do it the long way around. So we have a binomial times a binomial. You can use the aide-memoire FOIL if you want. We will multiply 2x by 2x, 2x by minus 3 divided by x. And then we will multiply minus 3 divided by 2x by 2x. Then minus 3x divided by x multiplied by minus 3 divided by x. All this gives us 4x squared minus 6x divided by x minus 6x divided by x plus 9 divided by x squared. Here we have to cancel the x's in the middle term, which gives us 6 minus 6, but do not cancel the x squared. I know it seems very tempting to do that, but you cannot cancel across an addition or subtraction sign. And so we have our final answer, which is 4x squared minus 12 plus 9 divided by x squared. That's it for this week. On the next episode, we're going to tackle factorizing binomials and trinomials, and we're going to revisit the material that we covered on this episode with some more practice questions. So let me know how you found it. Was it too simple? Was it too slow? Do you want to hear more about neurosurgery and incorporate more about that in the next episodes? Let me know in the comments section. Please like and subscribe if you enjoyed this. This has been Dr. Lunga's Math Lab. Bye bye.